day, I'm Dr. T and welcome to my office. So today I'd like to talk about bonds. So when we're dealing with organic chemistry, we're going to be dealing with carbon bonding to a whole lot of other things, as well as things that aren't carbon bonded to other things that may or may not be carbon. Well, it's actually very important to understand how atoms bond in order to understand this. And for organic molecules, typically we're going to see one of two types of bonds. Generally, the most common type of bond is the sigma bond. And in this case, you're going to have your two atoms, and those atoms are going to merge their atomic orbitals and form a molecular orbital. Or I should say molecular orbitals, but we're only going to be talking about one of those molecular orbitals at a time. So the one that we usually see in a single bond is going to be a sigma bond. And in this case, you've got your two atoms, and the molecular orbital is such that the electrons are mostly located between the two atoms. Basically the way you would think a bond would be. With this, the bond won't bend, or it doesn't like to bend, but it can rotate. Now bonds will, by the way, they will bend, they will flex, they will do a little bit. But typically they don't do much. But with sigma bonds, those things can rotate freely. There's no hindrance to twisting. This is why when you draw a molecule and you could rotate the molecule into something else, that's not an isomer, it's just simply a different configuration. Now, that is one type of bond. The other one that you commonly see in organic molecules is known as the pi bond. The pi bond is typically seen as the second or third bonds in a multi-bond. So if you have a double bond, one of those two bonds will be a sigma, the other will be a pi. If you have a triple bond, one of them will be a sigma, the other two will be pi bonds. Now with a pi bond, the molecular orbitals cannot have the electrons in between the two atoms because that's where the sigma bond is. The electrons don't want to coexist with other electrons. They're all negatively charged. So instead, the pi bond is going to bracket the sigma bond. It'll be above and below the sigma bond. Not above or below, but actually above and below. It kind of forms this kind of circular or lip shape, for lack of a better word. Now, because the pi bond is both above and below, it's not along the axis between the two atoms, it's not going to twist. So if you have a double bond and, say, rotating that double bond would change the configuration of your molecule, then those will be isomers, and those will be distinct molecules with very similar but not identical chemical and physical properties. Now, a couple other points to consider when we talk about pi bonds. Pi bonds are not quite as strong as sigma bonds, which is why double bonds are stronger than single bonds, but not twice as strong as a single bond. Additionally, if one atom has two pi bonds, those two pi bonds will be rotated by 90 degrees. So for a triple bond, you'd have a single bond in the middle. It would be bracketed above and below by one pi bond, and then from side to side by the other pi bond. If you have a carbon that has two double bonds on it, then one pi bond would be going, up and down. The other one would be going side by side. This is going to have some connotations for the next property of pi bonds, and that is because they are going above and below the carbon. If you get pi bonds next to each other, so not sharing the same carbon, because those would be rotated by 90 degrees, but if you have, say, carbon 1 and carbon 2 have a double bond, carbon 2 and 3 have a single, and then carbons 3 and 4 have a double bond, then you may very well have a situation where the double bond between 1 and 2 and the one between 3 and 4, those pi bonds that are involved with it will line up, and when they do, the electrons can actually be shared between all four carbons. This is called conjugation. And when it conjugates, you get some rather interesting molecular orbitals. And you will see this quite often in chromophores. So molecules or parts of molecules that are able to absorb light, if you can conjugate several pi bonds together, so several double bonds all in this kind of double single pattern, this will allow those pi bonds to conjugate, and you can get an energy gap between the ground state and the lowest excited state that will allow for, say, visible light to cause that jump. Thus, you can get a lot of your dyes, a lot of your organic molecules that absorb the light in the visible spectrum are going to have this conjugated system. Now, there's another interesting quirk with conjugation. If you are able to get a conjugated system and put it in a ring, most often you're going to see this in 6-carbon rings. So imagine a hexagon, every other bond is a double bond. This is going to conjugate, you're forming a loop. All of a sudden it's like, where's the every other? These are going to not only do the conjugation, they're going to do a resonance structure, and this is going to create this interesting pi system. This gives a couple of important features. One, this is going to cause an incredibly stable molecule, because not only are you going to have to break a double bond, but you're going to have to disrupt this entire pi system. So these structures that we call aromatic, because there are several compounds that have a nice smell, although by no means all of them that has this structure. These are called aromatics, and they are going to be very, very stable. Now they'll do some rather interesting features. They're an interesting flatness to them, which allows them to interact with other aromatic molecules. The last part of interest when it comes to aromatic rings is that they can do weird things with electrons, so their chemistry will actually be somewhat different. So an oxygen hooked onto an aromatic ring is going to behave differently than an oxygen hooked onto a carbon that's not in an aromatic ring. And if you have large networks of aromatic rings that are all interlinked together, like you see in graphite, you can actually conduct electricity because this entire pi system will go out through the entire interconnected series of aromatic rings. And, well, this allows electrons to travel, and traveling electrons is the conduction of electricity. So with that said, understanding the core features of bonds is a useful thing for the chemist, and it does help us understand what's going on. So with that said, have a wonderful day, and I'll see you in later videos.